intermediate value theorem. This is our first gang sign. This is IVT. We will get lots of them very soon. All right, so this is our first gang sign. We will have many. We will have IVT. We will have MVT. We will have AVT. We'll have FTC1, FTC2. I think I'm missing one. EVT. We'll also have EVT. So we'll have lots of different theorems this year. And so this is our first one that we get to talk about. All right, so intermediate value theorem. Let's read. And Gail's going to be our reader. Go for it.
If f is continuous.
Continuous. What does continuous mean?
That the limit as x approaches c equals f of c.
Good. The limit is equal to the value. So it has to meet that condition. Keep going.
If f is continuous on a closed interval a, b, f of a does not equal f of
All right, let's stop there. What does f of a not equal f of b mean?
That
Yes,
that it's not the same y value.
not the same y value. So we have differing y values. Good. Keep going.
Okay.
And k is any number between f of a and f of b, then there is at least one number c in a, b such that f of c equals k.
All right, fantastic. So this is called an existence theorem. It means something will exist on it. All right. Has anybody ever played monkey in the middle? Has anybody ever played monkey in the middle? All right, Yamil's played monkey in the middle. That's good. All right, so when Trace Lane and Yamil played, and Yamil's the monkey. All right, and so Yamil is in the middle, isn't he? And so this is how it's working, though. The function has to be continuous. In layman's terms, that means you can draw it without lifting your pencil.
Yes.
Yeah? And then I have differing y values. So if I were to have y values, like say this one goes up here and that one go down there, and then it's continuous, I can draw it anywhere. I will have at least one time I will have a monkey in the middle. At least once. All right? Now, in this case down here, how many times did my monkey in the middle cross? This one crossed 3. 1, 2, 3. All right? This one crossed 3 times. However, it's at least how many times? Once. All right? If it meets those criteria, that's what intermediate value theorem does. However, let's look at this guy. What's wrong with this one?
It's not continuous.
It's not a continuous function. Okay? There's a jump. That's beautiful. Great language. I like that. All right? So I have differing y values, yes? So that criteria was met. However, the function wasn't what? Continuous. Therefore, I might not have something in the middle. Now, could it have something in the middle? What if it crossed there? Could it?
Maybe.
Yeah, maybe. But must it?
No.
No. And so that's the biggest thing here. All right, let's do one. Haley's going to read for us here. Use the
intermediate value theorem to show that the polynomial function f of x equals x squared plus 3x minus 2 has a 0 in the interval 0, 1.
All right, fantastic. All right, so here's my function. And then this my interval is 0 to 1, so there's my a and b. And then it says it must have a 0. And so that's my monkey. That's my little dude in the middle. That's where I needed that. All right, and so this is like f of c is equal to 0. It doesn't have to be a 0, but this one we said it is. All right, it could have said like the value is 1. All right, and so my monkey would be f of c equals 1 in that case. Does this make sense? All right, so we need to have a what kind of function though? Continuous function. Now, this is a polynomial. Polynomials are very well behaved. Our polynomial is always going to be continuous. Yes. So, we need to say that f of x is continuous on the interval 0 to 1. Now, remember talking about that reciprocal function, that 1 over x? Was 1 over x continuous?
No, it breaks it.
It breaks only at what though?
0.
0. But if my interval were like 2 to 5, would it be a continuous function?
Yes.
Yes, because it's on the interval 2 to 5. Because 0 is not part of that interval anymore. So that would still be a continuous function. So this is continuous. So yay, we have my monkey in the middle. Now what do we need? Differing what? Y values. So now we need to find our y values. So how do we find our y values? Please use the correct verb.
Sub in.
We need to substitute in. All right, so we substitute in 0. And so when we substitute in 0, what do we get for one of my y values? Negative 2. And then we substitute in 1. So what's my other y value?
1 plus 3 minus 2, so 4 minus 2. 2.
2. Beautiful. All right. So is the monkey in the middle?
Yeah.
Yes, so 0 is in between negative 2 and 2. And that's where we need to show an inequality. So we just say negative 2 is less than f of c, which is equal to 0, which is less than or equal to 2. And I like to throw a gang sign, even though AP will never score the gang sign. I will have my students throw up their gang signs often. All right? All right. So here's what I want to make sure of, though. Yes, we need to say it's continuous. Yes, we need to show differing y values. Yes, we put the monkey in the middle. However, it doesn't have to be the exact middle. Does everybody follow me on this? So if this is like negative 2 and this is 8, is 0 still in between negative 2 and 8?
Yes.
Yes. And so that would still be good. So this is the little graph from it. And so at 0, it's down at negative 2, and at 1, it's up here at 2. Now, it says it crosses somewhere in between, what, 0.4 and 0.6 or something like that?
Probably say so.
Because did we actually find out when it's 0, though? No, it just says we proved it existed. All right, and so that's what intermediate value theorem is doing. All right, so this is 1.5 infinite limits, and I need a good reader. Oh my gosh, Mr. Moore, go for it.
All right. 1.5 infinite limits, a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit.
An infinite limit. And I want to talk about the word infinity, or the concept of infinity. Infinity is a behavior or a direction. All right. And so as I go to the right, that is infinity. As I go up, that is infinity. As I go left, is this way left for you? Okay, that's negative infinity. As I go down, that's also what? Negative infinity. It's actually a descriptor rather than like a number. All right. Now, sometimes we think of infinity as a number, which will help us. However, it's really a direction or a long-term behavior. Okay. So that's really what's happening here. All right. So let's look at this function. We have this function 3 over x minus 2. Where does it break?
At x equals 2.
At x equals 2. It breaks at x equals 2. Why? Why does it break at x equals 2? It's a number over 0. And so what created that number over 0? What makes it? It's a vertical asymptote. And so what we're going to do today is we're going to take a limit as x approaches from the left, where I hit a vertical asymptote, and we're going to do a limit as x approaches 2 from the right when we had a vertical asymptote. Now, before in our chapter this year, if we had a vertical asymptote, what do I know my limit does?
Breaks.
It doesn't exist, right? When does it not exist? It's either doing what? Increasing or decreasing without bounds, or possibly both. And so now we're going to be the descriptor of that thing. All right, so let's do it. So now we're going to do 2 from the left. So if I were to substitute in 2 from the left, what do I actually think of?
3 or no?
No, you do
Like 1.999, a little bit less than 2. Okay, and so now I have a positive number of a 3 over something a little less than 2 minus 2. So what do I have on the bottom here? A really small negative. So I have a positive over a really small negative, which is what? Negative infinity.
Look at that.
So now we're going to go from the right. So we're going to go to a little bit positive of 2. So like 2.01. So I have a positive over a really small what? Positive, which makes it what? Positive infinity. All right? All right. All right. So before we would say does not exist, increases without bounds, or does not exist, decreases without bounds. That is still a sufficient answer. Does everybody hear me on that? However, if it's a multiple choice question, they're more likely to have the descriptor than does not exist, increases without bounds. They'll say infinity. However, they mean the same thing. So if this is a free response question, it won't be on your AP exam, but it might be on my test. Could you give me either one?
Yes.
Yes, and I will accept either one.
So
All right?
We're good just leaving it like that.
I'm good with just leaving it like that. All right? All right. The other thing I want to talk about is the only time you go a little bit left and a little bit right is when you get a number over 0. It's the only time you use your new tool in your toolbox is when you get a number over 0. All right? The other ways we're going to do like fractions and those things. All right? All right. Here we go.
No more fractions, please.
They'll happen again. All right, so let's look at this one. So I have a limit as x approaches 1 of 1 over the quantity x minus 1 squared. So what happens at 1? I try to direct substitute because that's what I try to do every time. What happens?
Number over 0.
I get a number over 0.
Means,
So I have a vertical asymptote. So what do I need to do?
let's do it. Go a little bit smaller and go
go a little bit left and a little bit right. Exactly. So let's do it. And so I need to go from the left of 1, and I need to go from the right of 1. All right.
Let's do,
So if we substitute a little smaller, what does that become?
Positive.
A really small what? Negative. And then what happens to it?
Squirt.
I squirt.
It's positive.
So now it's a really small what? Positive. So I have a positive over a really small positive, which makes it positive infinity. All right. And then let's do it again. As we go from the right, I'm going to have a really small what on the bottom? Positive. So I have a positive over a really small positive, which makes it positive infinity. So this limit statement is infinity. Or you can say does not exist, it increases without bounds. Okay? All right, let's look at this next one. So I know we have a picture, but honestly, you probably not have pictures, so I kind of want you to just look here. The picture helps us like see if we're right. All right, so let's look at this next one. So I have a limit as x approaches 1 from the left of negative 1 over x minus 1. If I substitute in 1, what happened? I get a number over 0.
Just open it, but he's not.
So I go from the left. So how do I think of 1 from the left?
A little bit less than 1.
A little bit less than 1, so 0.99. Exactly. So now I have what up top?
Negative.
Negative over a really small what?
Negative.
Negative, which makes it
Positive.
positive infinity. So now let's go a little bit from the right. So a little bit more than 1. So when I go from the right, I have a negative over a really small what? Positive, which makes it what? Negative infinity. Now I want to go a little further on that one. What if I say the limit as x approaches 1 of negative 1 over x minus 1? What's my answer?
Does not exist.
Does not exist, because why?
Increases and
It increases and decreases without bound. All right, it has to be that way. I can't call it negative infinity and infinity, because the limit is when you actually go from what? Both sides. All right, these, yeah, very, very good. All right, but those are going from the left or the right, and so we can actually give descriptors on that. All right, well, let's keep moving. Here we go. So on this one, I just really want to talk about like what a hole is and what a vertical asymptote is. So what's a hole? What makes a hole? 0 over 0. All right, and so something canceled and it creates a hole. Does that mean a limit doesn't exist? No, I'm going to get a simpler function and then figure it out from there. All right, so then we get a vertical asymptote. When do we get a vertical asymptote? A number over 0. So when we get a number over 0, I need to explore further. How do I explore further on that one?
by going a little left.
Little left and a little right. All right, and you need to figure out which tool you use when. All right, so when you get a hole, you either factor, you rationalize, you do the fraction thing. All right, if you get a number over 0, you're going a little left and a little right. Okay, so that's when you use your tools. All right, cool. Let's move. All right, so let's look at this one. I got 1 over, you know what? We don't even need A. Are we cool with that?
Yeah.
Let's just skip to B. All right, so this first one, we got x squared plus 1 over x squared minus 1. All right. So what do we like to do to quadratics?
F them up.
We like to F them up. What can we F up the top though? No, can we F up the bottom?
Yeah.
Yeah, let's do it. And so let's factor it. So what does it factor to?
X plus y minus 1.
You guys are so smart. So what do we get? When do we get vertical asymptotes here?
When x equals.
So we get vertical asymptotes when? At x equals -1 and x equals 1. And so because I got a vertical asymptote, I get numbers over zeros. I need to go a little left and a little right. And so we're going to deal with -1 first. So I'm going to do a limit as x approaches -1 from the left, and I'm going to do a limit as x approaches -1 from the right. All right, cool. So if I go a little from the left, all right, and I substitute in. If I substitute in -1 from the left, that's going to be a little bit more negative than -1, right? So like -1.01. Is everybody following that?
Yeah.
All right, and so when I square it, is it going to be more or less than 1? It's going to be more than. So what do I actually get on the bottom when I square it? A really small what? Positive. Up top, I'm still going to get 2. Every single time we do this, we're going to get 2 up top. All right? And so I get 2 over a really small what? Positive, which makes it what? Positive infinity. All right, let's do it again. Now I go from the right of -1. So, like, how should I think of that? Negative 0.999. Exactly. And so now, what do I get? I get 2 over what? A really small negative, which is going to make it what? Negative infinity. All right? And so now we're going to do the same thing as we approach 1. So I'm going to do a limit as x approaches 1 from the right. Oh, sorry. I should go left first. Left. It doesn't really matter, but I'm just going to go in order. All right. I just think you should do left first because, like, that's how we think. We go left or right. But anyway. All right. I think Asian countries do too. But anyway. All right. So here we go. So we have 1 from the left. All right. And so what do I get up top? I get 2 still, right? But what do I get on the bottom when I substitute in 1 from the left? I get a really small what? Negative. So that becomes what? Negative infinity. And then if I go 1 from the right, I still have 2 up top, and then it's over what? A really small positive. So that becomes what? Positive infinity. So I have vertical asymptotes at -1 and 1. However, this is actually how it's moving. It's going up. It's going up to infinity from the left, and then it's going down to negative infinity from the right, just like we did there. And then it's going down to negative infinity from the left, and then it goes up to positive infinity from the right. Do we see how that worked? We're going to do some trig. So now we have cotangent. All right, so that unit circle is still going to come into practice here. This is good. All right, so how do I think of cotangent? Cosine over sine, exactly. Wow, that was crazy. All right, so I got cosine over sine. So how do I get a vertical asymptote? When sine is equal to what? 0. So when is sine 0? 0, pi, 2 pi, so forth, right? And so I'm going to just say 0 and pi for this thing. All right, so I got my vertical asymptotes at 0 and pi. I'm just going to do one of them. Are you cool with that? And I'll talk about the other one. Which one do you want to do, 0 or pi? 0. Let's do it. All right, so now I'm going to do a limit as x approaches 0 from the left, and I'm going to do a limit as x approaches 0 from the right. So this is 0 right here, and this is pi. Yes? Does everybody agree with their unit circles? Does everybody understand? Okay. So when I go from the left of 0, it's actually like right here. Okay? Because we haven't gotten there yet. All right? So left of 0 is down here. All right? Cosine deals with the what value? The x. Sine deals with the what value? The y. So my cosine value is a big positive. Okay? Because we went right. It's almost 1. All right? However, my sine is actually a really small what? Negative. So I have a positive over a really small negative, which is negative infinity. So as I go from the left, I get negative infinity. All right, and so then as I go from the right, it's just a little bit more positive of 0. So my cosine is a really big positive, and then my sine is a really small positive, which makes it positive infinity. I just want to talk about pi real quick without actually writing it down. If I go right of pi, it's up here. If I go left, just kidding. If I go left of pi, it's up here. And if I go right of pi, it's right there. Okay? Because it's a little bit less than pi and a little bit more than pi. All right? Does that make sense? All right. Cool. So this is why our graph of cotangent, I can't get it now. All right? This is why our graph of cotangent, all right, looks like that. All right. This is our last one. So we're going to determine all the vertical asymptotes. We'll talk about the holes as well on this one, and we'll work with them. So we need vertical asymptotes and the holes. So we have x squared plus 2x minus 8 over x squared minus 4. So we have some quadratics up in her. What do we like to do to quadratics, Mr. Roberts? F them up. So you are a factoring machine. So what does it factor to?
X plus 4, x plus 4, x minus 2.
Oh, me.
Yeah.
Oh, x plus 4, x minus 2.
Love it. All right. Whoa, what is going on? All right. And then what's on my denominator? What does that F up to? X plus 2x minus 2. All right.
We have a. Say it.
So what happens? What happens? The x minus 2's cancel, right? What did that create? It created a hole. Now, this created a hole at what? At x equals 2. So this is why we have a limit. All right? So now I can take a limit as x approaches 2 to figure out where that hole is. And I'm going to use my simpler function of x plus 4 over x plus 2. Okay? Because that's the whole reason why we do these limits. So, let's figure out the y value. So if I substitute in 2, what do I get? 6 over 4, which can simplify to 3 halves. So I actually have a hole going on at 2 comma 3 halves. All right?
Oh, interesting.
That's how we get the y values. That's it. All right. So now, where do I have a vertical asymptote?
At -2.
At x equals negative 2.
Go, you know.
And so now I'm going to do, how do I do a limit now?
Okay, well, we know it to be a. So
A little left and a little
right.
right. So now I do a limit as x approaches negative 2 from the left. And actually, I'm going to use my simpler function. I'm going to do this x plus 4 over x plus 2. And then I do a limit as x approaches negative 2 from the right. Now, could you actually substitute in to the original?
Yeah.
You could. However, I'm not that smart.
Pay for convenience.
All right. All right. Yamil can do quantum mechanics, but I am not that smart. And so now, if we substitute in negative 2, what do we get up top?
2.
We get 2. But on the bottom, I actually have to do negative 2 from the what? Left. So I have 2 over a really small what?
Positive. Guys.
A really small negative, which makes it what?
Whoa. Oh, because it's
Negative.
Negative infinity.
Oh, I did it because.
And then I need to do negative 2 from the right. So up top, I'm going to have a what again? 2. And then on the bottom, what am I going to have?
Positive.
A really small positive, which makes it what?
Positive.
Positive infinity. So our graph should look like this. And so we have vertical asymptote at x equals negative 2. However, when I go from the left, it should go down, just like we did here. And then as I go from the right, it should go up, and I have a hole going on at 2 comma 3 halves. All right?
Are you ever just going to give us
So page 88, numbers 2 through 12 even,
See, originally this was planned for
13 through 36 all.